Right now, somewhere on Earth, a chemist is being paid millions of dollars to fail at making one single color blue. That's it, just blue. And in the next 10 minutes I'm going to show you the actual atomic reaction happening inside every firework, why red is easy, why blue is nearly impossible, and why the cool color you loved as a kid is secretly the hardest problem in pyrotechnic chemistry. Stick around, because by the end, you'll never watch a fireworks show the same way again. Most people think fireworks get their color from paint or dye, or some kind of colored fire gas. Wrong, completely wrong. There is no blue chemical. There is no red flame gas sitting in a canister. What's actually happening is something far stranger. You are watching individual atoms get so violently disturbed that they scream light back at you. And the color of that scream depends on one thing: which metal you used. That's the secret. Fireworks aren't colored. They're excited, literally. Here's what's really happening, atom by atom. Every firework shell is packed with metal salts, compounds like strontium carbonate, copper chloride, barium nitrate. When the black powder detonates, it doesn't just create an explosion, it creates heat upwards of 2000 degrees Celsius. That heat slams into the electrons orbiting those metal atoms and kicks them into a higher energy state. But here's the part almost nobody explains correctly. Electrons hate being up there. It's unstable, unnatural. So within nanoseconds they fall back down to their original orbit. And when an electron falls, it has to get rid of the extra energy it absorbed. It can't just disappear. So it releases that energy as a photon, a single packet of light. The color of that photon isn't random. It's mathematically determined by exactly how far the electron fell. Bigger fall, more energy. Bluer light. Smaller fall, less energy. Redder light. This is called atomic emission, and it's the exact same physics NASA uses to figure out what distant stars are made of just by looking at their light. You're not watching a fireworks show. You're watching quantum mechanics on a public holiday. Let's break down the actual periodic table hiding inside every firework. Red, the most reliable, most intense color in pyrotechnics, comes from strontium. Strontium's electron transitions release light at almost exactly 641 nanometers, which sits deep in the red zone of the visible spectrum. This is also why old emergency flares are strontium-based. It's not just pretty, it's engineered to be seen through smoke, fog, and long distances. Green comes from barium, specifically barium chloride, which produces a tight, narrow emission around 524 nanometers. Chemists actually consider green one of the more pure colors because barium doesn't leak much light into other wavelengths. That's why fireworks green often looks more saturated than any other color in the sky. Yellow is sodium, the same sodium that's in your table salt. If you've ever accidentally spilled salt on a stove flame and seen it flash bright yellow-orange, congratulations, you've already done amateur pyrotechnics in your kitchen. Sodium's emission is so strong that even trace contamination can wash out other colors, which is actually a massive problem for firework manufacturers trying to make pure colors like blue. Purple isn't even a real element color, it's a cheat code. Purple is created by combining strontium red and copper blue in careful ratios, tricking your eye into blending the two emissions into violet. There is no purple electron transition in nature's toolbox. Purple is chemistry's optical illusion. Now here's the part that separates casual firework watchers from people who actually understand the chemistry. Blue is the hardest color in pyrotechnics, not close. Blue comes from copper, specifically a molecule called copper monochloride, CuCl. But copper's emission is a nightmare to control for one brutal reason. It only glows blue within an incredibly narrow temperature window, roughly 1000 to 1200 degrees Celsius. Too cold, and the copper compound won't even ionize, you get nothing. Too hot, and this is the part almost nobody knows. The copper chloride molecule breaks apart entirely before it can emit blue light, and instead you get a washed out white or pale green. So pyrotechnicians are threading a needle inside a controlled explosion, trying to keep a chemical reaction inside a 200-degree range while everything around it is detonating. It's like trying to keep a coffee at the exact perfect temperature while it's sitting inside a bonfire. This is why, even today, deep true blue fireworks are considered the gold standard of pyrotechnic skill. Some Japanese firework masters famous for a shade called Japanese blue guard their exact copper formulations like state secrets, because getting blue right can define an entire company's reputation. You've been unknowingly watching one of the hardest solved problems in applied chemistry every New Year's Eve of your life. Quick myth bust before we go further. Those bright white sparkling trails you see, the crackling, shimmering tails behind a firework, those aren't emission colors at all. That's incandescence. It's a completely different mechanism. Tiny particles of metal, usually aluminum, titanium, or magnesium, are literally burning white hot, the same way a metal filament glows in an old light bulb. It's not electrons jumping energy levels. It's just raw heat being radiated off burning metal dust. So every fireworks show you've ever seen is secretly running to separate branches of physics simultaneously. Atomic emission for the color, and thermal incandescence for the sparkle. Nobody tells you that. Most fireworks companies won't even explain it because it sounds too technical for a marketing brochure. Here's why this isn't just trivia. The same atomic emission principle that colors a firework is used to identify elements in exploding stars light years away. It's used in your kitchen stove's flame test. It's used in forensic labs to identify unknown metal samples. It's used in factories to monitor molten metal temperatures in real time. The sky show you watch for 90 seconds is running on the exact same physics that lets scientists read the chemical fingerprint of the universe. So next time you're staring up at a fireworks show, you're not just watching an explosion. You're watching trillions of electrons falling back to where they belong, screaming out photons and colors decided purely by the periodic table. Red is strontium, green is barium, yellow is sodium, purple is an illusion, and blue is still one of the hardest reactions humans have ever tamed. If this blew your mind,